Hello students, today we are going to discuss the derivation of laws of refraction using Fresnel's principles. First of all, what is refraction? When light from one medium enters into another medium, at the point of contact or at the boundary of the two medium, the light ray bends and moves with another velocity in the second medium. This is called refraction of light. If light travels from a rarer medium to a denser medium, it will bend towards the normal. And if light travels from a denser medium to rarer medium, it will bend away from the normal of the boundary. Let us remember Fermat's principle. According to Fermat's principle of extremum path, when light ray travels from one point to another through a set of medium, of all the possible paths, it will choose that path for which time taken is extremum. That is, time taken can be a maximum, minimum, or stationary, depending on the cases. In this case, we will be using time taken to be minimum. Let us assume the case of a refracting surface. Here, I have drawn a plane M1, M2, M3, and M4, which acts as the boundary between a medium of refractive index mu1 and mu2. Let a light ray from point A be incident on the refracting surface and get refracted towards point C. The light ray can refract upon any point on the surface of M1, M2, M3 and M4. So the point of refraction can be anywhere on this XZ plane, which is shown on the left side of the figure. So M1, M2, M3, M4 is actually the XZ plane, and the point of refraction can be anywhere on that surface. I'm drawing normal from A to the surface. Let us call it point O. And another normal from C to the surface. Let us call that point Q. This point can be called as B. To show an arbitrary path followed by the light ray, I am going to choose another point K upon which light gets refracted. Now let us try writing the coordinates of these points. A is at the origin of this system is at O, and A is at a distance of small a from O. Q is at a distance of small c from O. B is at a distance of x from O, and K is at a distance of z from B. C is at a distance of small b from Q. So using these values, let us try writing the coordinates of these points. Coordinates of A can be given as 0, A, 0. Coordinates of K can be given as X, 0, Z, and the coordinates of C can be given as C minus B, 0. Okay. Following Fermat's principle, we have d delta by ds is equal to 0. That is, the rate of change of path length must be minimum. Least possible value of minimum is 0. The path length here is defined as product of refractive index into geometrical length. Here the light ray is traveling through two mediums. Hence path length should be calculated in two mediums separately. The first medium, the optical path length, is given as mu1 into AK. We are using the light ray path AKC. Hence, the path length in first medium is mu1 AK plus the path length in the second medium is mu2 KC. This can be written as mu1 into AK can be written as square root of x minus 0 the whole square, that is x square, plus 0 minus a the whole square, that is a square, plus z minus 0 the whole square, that is z square, plus mu2 into kc, that is c minus x the whole square, plus minus b minus 0 the whole square, that is b square, plus 0 minus z the whole square, that is z square, whole raised to 1 by 2. Here the path length L will be the optical path length itself, delta, because the medium of refraction should be taken into consideration. Since the light ray can vary along x and z axis, we take Fermat's principle along both the x and z axis. So first let us calculate the derivative of this optical path length along the z axis, keeping x a constant value. First we can write dou L by dou z at x a constant value is given as constant mu1 into derivative of this AK term. AK is given as, you can see in this expression, AK is given as x square plus a square plus z square whole raised to 1 by 2. So the derivative of that term will be 1 by 2 into 1 divided by x square plus a square plus z square whole raised to 1 by 2 into 2z plus second term mu2 into 1 by 2 into 1 divided by c minus x square plus b square plus z square whole raised to 1 by 2 into 2z. Okay. 2 and 2 cancels out. We get mu1 divided by x square plus a square plus z square whole raised to 1 by 2 plus mu2 by c minus x whole square plus b square plus z square whole raised to 1 by 2, this term into z. So according to Fermat's principle, this is equal to 0, right? So the product of this term should be equal to 0 implies that either the first term or second term should be 0. Here in the first term we can see that mu1 is not 0, it is a positive number being refractive index of a medium. Mu2 is again a positive number, it cannot be 0. Refractive indices have the least possible value of 1, that is of air. Here A is defined as a positive number, distance of point A. C is defined as a positive number, distance of C. B is defined as a positive number, distance of point B. Sorry, C from the y-axis. Here, this implies that the first term cannot be 0 and hence in turn Z must be equal to 0. That is light ray can refract only upon the condition that Z must be equal to 0. It implies that light can vary along x, but here along the z-axis it should be 0. That is, it can only vary along this line, right? It can vary only along this line. And that shows that the incident ray, the refracted ray, and the normal to the refracting surface all lies on the same plane. And that is the first law of refraction. The incident ray, refracted ray, and normal to the boundary of incidence all lie in the same plane. Now let us derive the second law of refraction. For that, we are using the partial derivative along x-axis. Dou L by dou x at a constant value z, we got it as 0, is given as mu1 into 1 by 2 into 1 divided by x square plus a square plus z square. No need to write z square, right? Because z is 0. Okay, fine. That is a square plus x square whole raised to 1 by 2 into 2x plus mu2 into 1 by 2 into 1 divided by c minus x the whole square plus b square whole raised to 1 by 2 into 2 times c minus x into minus 1, right? That is from c minus x that we get minus 1. According to Fermat's principle, this derivative should be equal to 0, right? Here 2 and 2 cancels out in both terms. We get mu1 into x divided by x square plus a square whole raised to 1 by 2 is equal to mu2 into c minus x divided by c minus x the whole square plus b square raised to 1 by 2, right? Now let's go to the figure again. We have a relation in angles here. From this figure, we can see that x divided by root of x square plus a square will be sine I. Okay, likewise, c minus x is defined as the distance between B and Q. Distance between B and Q is c minus x. C minus x divided by square root of c minus x square plus b square is the hypotenuse, and that gives sine r. Okay, so coming back, I can rewrite this as mu1 sine I is equal to mu2 sine r. Hence, sine I by sine r is equal to mu2 by mu1. And this is the second law of refraction, where it is stated as the ratios of sines of angle of incidence to the angle of refraction is equal to the ratio of refractive indices of the two mediums. This is also called Snell's law. That's all for today. Thank you.